Okay, so last time we started this new concept of de-randomization, which is basically the question of BPP equal to P. BPP is the class of problems that are solvable in randomized polynomial time. P is the class of problems solvable in deterministic polynomial time. Whether these two sets are the same. Okay, in other words, can randomness be eliminated in an efficient way? So this theorem on the slide, proved by Carbonates and Impagliazzo, is what we are interested in, which shows that if BPP is equal to P, then there is hardness in nature. It's an either or statement. One of these at least has to be true then. Okay, either next doesn't have Boolean circuits, small circuits, or permanent doesn't have arithmetic circuits, again small. So before embarking on the proof of this, which will be quite complicated and long, let me give you some hint about this connection by a different theorem. So meanwhile, we prove a simpler connection as a detour. So this is an old result due to Heinz and Schnorr. From the 80s. So this says that if black box PIT is in P, okay, so what is black box PIT? Black box PIT means this question of polynomial identity testing that we defined before, checking whether a given circuit is 0. It's the same problem you want to solve, but now the circuit, the details of the circuit you cannot see. Okay, so the circuit is given as a black box. So all you can do is you can either basically you can just evaluate the circuit at some points which have to be prefixed. You have compute these points in advance, and then given any black box, you compute the value of the black box on these points, pre-computed points, and check whether the black box computes non-zero. If it does, then the black box is non-zero, otherwise the black box is 0. So that problem, again, this has a very simple randomized practical algorithm. You just pick your points randomly and evaluate your black box. But is there a deterministic polynomial time algorithm? So Heinz and Schnorr showed that if you find a deterministic polynomial time algorithm for black box PIT, then there exists an E explicit polynomial family which is exponentially hard. Okay, so the two important things here are, first is obviously we want a hard polynomial family, but at the same time we also want it to be explicit. Okay, so what this theorem is saying is that if you can solve black box PIT in a de-randomized way, then you will have an explicit polynomial family which is hard and very hard. Okay, so let us prove this. This has a simple proof, surprisingly. So this is again the connection between de-randomization, or this you can think of as the first connection between de-randomization and hardness, or proving lower bounds. So how do you do this? Well, suppose you have designed a set of points P1 to Pm in f to the n for black box PIT. Of n variate size S. So these points that you have pre-computed are P1 to Pm, right? They have n coordinates. So the property of these points is it is solving black box PIT in P, right? So they are efficiently produced, and a non-zero circuit of size S will evaluate to non-zero on one of these points, at least one of these points, say at Pi will be non-zero. So what we will do is, we will let us define a polynomial which vanishes at all these points. So what will you know about that polynomial? You will know that that polynomial which vanishes on all these points cannot have size S. It has to have size more than S. Okay, so that is the potentially hard polynomial. So let us do it a bit more systematically. So we'll construct, or we'll find polynomial A in L variables where L is, let's say, log S, double that plus 1. So we'll find a polynomial A whose number of variables is around log, okay, log of S, such that for all these points 1 to m, A vanishes. Okay, so this polynomial we'll call an annihilator. That's the goal. So let us try to find a polynomial A which vanishes on all these m points, an annihilator polynomial. So if it exists and it is explicit, then this is a good candidate for hardness, right? Because this circuit cannot have, this polynomial A cannot have sizes circuits. Remember, if it had sizes circuit, then it cannot vanish on all the points P1 to Pm, right? So let us just now look at the properties of this polynomial. What are the parameters? How explicit is it? How hard is it? And whether it exists, right? And actually we will also ensure that this is multilinear. So let's do that here. So multilinear polynomial A will have what? Will have coefficients A e bar, y bar, e bar for all e bars 0, 1 to the L. Okay, so we are actually thinking of A as a multilinear polynomial, which means that y1 square, y2 square or yl square, they don't appear. Okay, just individual degree 1 monomials appear. So y1 appears, y2 appears, or y1 times y2 times y3 appears, and so on. So this A e bar, these are the unknown coefficients. Has unknown coefficients these are the coefficients we want to find such that A at Pi is 0. So the constraints are that for all I 1 to m, E at Pi vanishes, right? So this means that there are m constraints So you can think of m, m in general will be polynomial in S, but you can think of it as S square. Okay, so there are m constraints above, and there are how many unknowns? So E bar, how many E bars are there? 2 raised to L. Each constraint is just giving you a linear relationship between A bars. So each constraint is linear. Right, and here you can see that since 2 raised to L is more than m, so you have more unknowns than constraints, and these constraints are homogeneous. So it's a linear combination of A bars equal to 0, right? There is no constant term. And there are fewer constraints than there are unknowns. So there is a solution. The system has a solution. And that gives you the A. Okay, so by solving the linear system, which is this, so by solving the linear system given to you by equation 1, you will be able to find A. How fast can you find it? Well, you can find it in so A can be found out in polynomial in. So this is 2 raised to L cross 2 raised to L matrix, right? So in terms of the matrix, polynomial in that. So polynomial in 2 raised to L. L was log S kind of, right? So this is polynomial in S time. Okay, so the coefficients of A, I should say coefficients of A. So these A bars, okay, they can be computed in poly S time. So in terms of L, this is actually E explicit. Okay, so with respect to the L parameter, which is the number of variables that polynomial A has, this is an E explicit polynomial, and this you can compute immediately from the or using the points P1 to Pm. And how hard is this? So E y1 to yl cannot have size S circuit, right? The proof is very simple. This is just because else E at Pi won't vanish. Right, since we have picked a polynomial that vanishes at all Pi's, by the property of Pi's, E should have size more than S, which means that this polynomial A is 2 raised to omega L hard, and 2 raised to L, So let's say big O of L time explicit. And how many variables does it have? L variables. Okay, so this finishes the theorem of Heinz and Schnorr, that if you can solve black box PIT optimally, then you have this L variate polynomial, which is 2 raised to L time explicit, and it is 2 raised to L size hard. Okay, so I hope that this theorem with a small proof convinces you that there is a strong connection between polynomial identity testing, so PIT, and existence of hard polynomials that are explicit. Okay, so the proof of this is relatively easy because our assumption was that we can solve black box PIT, right? So we are actually solving PIT without even looking at the circuit. So that was a strong assumption. Now we will go back to our theorem or theorem of carbonates and Impagliazzo, which will only assume PIT in P. Okay, so this particular algorithm may even look inside the circuit, use the circuit gates to make a decision. So this is a weaker assumption. It's a weaker algorithm, and consequences will also be much weaker. Okay, you will get either next or permanent hardness, but the proof will not be so easy. So let us now start the proof. Okay, it will actually require many of these interesting techniques that you usually learn in the first course on computational complexity. So let's go back to proving the theorem by carbonates and Impagliazzo. Okay, from 2003. Okay, so first we will prove a lemma which will use the PIT algorithm on permanent. So if PIT is in P and permanent has arithmetic circuits, small ones. Okay, so let's look at the statement. So what we are saying is we are assuming PIT in P, and we are assuming the opposite of this conclusion. Okay. So suppose PIT is in P and the second conclusion is false, which means that permanent has arithmetic circuits. Then what happens? So then we will show that P raised to permanent is in NP. So this means that, so what this is saying is that any polynomial time algorithm that uses permanent as a subroutine it will, those problems which can be solved this way will be contained in NP. Okay, this is a very strange conclusion. We don't believe that this is true, because permanent actually, remember, permanent is as hard or even harder than computing, or it is as hard as computing a number of satisfying assignments. And what this conclusion is saying is that even that can be done in NP. So we conjecturally we don't believe this to be true, but if you assume permanent has small circuits and PIT is in P, then you actually get this. This is what we will show. So the idea is guess the small arithmetic circuit for permanent and verify using PIT in P. Okay, so the idea of this proof is first guess the small circuit. Why can you do that? Well, because you are assuming that permanent has a small circuit, so you can guess in NP, and then you verify whether your guess is correct using the PIT algorithm, and thus you have a chance of showing that P raised to permanent is in NP. Right? Remember, NP is the collection of problems where which can be solved by guessing and verifying. Okay, so the goal is to show that permanent is of a similar type. Okay, so what is this? All we have to show is this verification protocol, right? How do you verify? So what you have to observe is we can expand permanent of an n by n matrix so let's call it per sub n of the matrix A. You can expand it by the first row. Okay, so expanding by the first row. You could recall this from determinant. Determinant also expand, you can expand it by the first row or the first column. So what that means is that you look at the entries which appear in the first row, and then for each entry look at the corresponding minor, which will be an n minus 1 cross n minus 1 matrix, and look at the permanent of that. Okay, so that expansion will give you the following identity. So permanent of A is equal to expand by the first row. So E1I is the entry, ith entry in the first row. I will go from 1 to n, and then put the minor. So permanent n minus 1 okay, so that's the minor. So permanent expands like this. This you can do as an exercise. Do this exercise and recall the same or very similar expression that you get also for determinant. So what this now think of this expression as a recursive procedure. Okay, so given an expression for permanent n minus 1, you can derive an expression for permanent n by this. Okay, so this can be used to get a verification protocol. You basically look at the circuit that is given to you at n minus 1 cross n minus 1 matrix input, and then check whether this left hand side and right hand side are the same. So where this A prime 1I is the sub matrix of A, deleting row 1 and column I. Okay, so basically minor just means that you delete the first row and delete the ith column. What remains is a n minus 1 cross n minus 1 square matrix, permanent of that. So now, given a circuit C n minus 1 square, right? So so n minus 1 square is the number of variables in the minor. To compute the permanent n minus 1. So once you have this circuit, we can use the following verification protocol. So this is, you check whether C n square, the circuit computing permanent for n by n matrix that you have guessed, whether this is equal to A1I dot C n minus 1 square on the submatrix. Okay, so that's your recursive verification protocol. So this guess and verify process will prove that C n square A is indeed permanent of A by induction on n. So this is, I mean, you can go through this inductive proof. The idea is quite simple. The idea is just that when you apply this recursive definition on 2 cross 2 or recursive kind of equation on 2 cross 2 matrix, then you will exactly get the 2 by 2 permanent. Okay, so this C2 square will be written as C1 square. C1 square is just, you will just get an entry. And you can see that actually what you get on the right hand side in this green equation is the 2 by 2 permanent. Then you repeat this for 3 by 3 permanent. Okay, so you will see that this C2 square will be 2 by 2 permanent, C3 square will be 3 by 3 permanent, and so on. So by induction actually it is always true that if Cn square satisfies this recursive equation, then it is permanent. So this is actually a characterizing equation. So this 2 characterizes permanent. That's the point. Okay, this is a characterization of permanent. So you just have to verify this on the circuit. Okay. So what you have done till now is, for any problem in P raised to permanent, which means that that is polynomial time algorithm or polynomial time Turing machine using permanent as an oracle. Any such problem which can be solved using permanent as an oracle, what we can do is we can first guess the circuit Cn square for permanent, then verify it whether it is, so what you have guessed, whether it is correct or not, whether it is indeed permanent, right? Verify it by using PIT. Equation 2 is exactly an instance of PIT, right? You have circuit on the left, circuit on the right and you want to test whether they are equal. So you guess a circuit, verify it by PIT algorithm, which you are assuming exists, and then use Cn square instead of the oracle. Right, so oracle now can be eliminated from your polynomial time algorithm for L. You can in fact use this circuit, this arithmetic circuit. So what does that mean? This means that once you have guessed the right circuit, you have a deterministic polynomial time algorithm, right? And because of the guess, it's actually a non-deterministic Turing machine. So this means that L is actually in NP, which means that anything in P raised to permanent is in NP. Okay. And any problem in NP can obviously be solved using permanent, right? So this actually means that these two are equal. So what we have achieved is, in lemma 1 what we have achieved is, if we assume that PIT can be de-randomized and permanent has small circuits, then permanent is as good as being in NP. Okay, this is a very strong conclusion. We don't believe this to be the case actually, which suggests that we are making some wrong assumption, and our conjecture is that permanent doesn't have small arithmetic circuits. Okay, so this is the questionable assumption. We don't believe this assumption. So that is the first thing. It was relatively easy to prove. Now from this point, basically permanent being in NP, from this point we want to reach to next not in P/poly, right? That was the hardness. So remember that this conclusion is not a hardness result. We want to get to a hardness result, right? We wanted to connect PIT to some sort of hardness, either arithmetic or Boolean. So how do we get there from here? So what we have achieved is the strange assumption of permanent in arithmetic P/poly gives the strange conclusion P raised to permanent is in NP. So let's now make another strange assumption. Which is next is in P/poly. Okay, so we'll assume this, that next is in P/poly, and we'll try to get a contradiction, which will definitely mean that one of these strange assumptions is false. Okay, so either permanent is not in arithmetic P/poly or next is not in P/poly. So what will happen with this strange assumption is that we want to show from this we want to show that If nexp is in P/poly, then nexp is in P raised to permanent, which we have shown to be in NP. Okay, you want to actually put nexp in P raised to permanent, which you have shown to be in NP before in lemma 1, which is a contradiction. Which contradicts the non-deterministic time hierarchy theorem. Okay, so this will be the end. So if we would have contradicted non-deterministic time hierarchy, we know that nexp is actually bigger than NP, it's not equal to NP, and that will be the contradiction. Okay, so this contradiction would tell you that one of the strange assumptions is false. So this would mean that one of the assumptions is false. Okay, that is the plan of the proof. So this proof requires a lot of tools, quantifier based, and interaction based complexity classes. So quantifier based complexity classes, basic example is NP, because NP is kind of the key quantifier there is there exist, right? There exist a correct guess which can be verified by the verification or by the verifier. On top of there exists, you can throw in for all, right? And then based on there exists for all, you can actually have more complexity classes which will potentially be stronger than NP. They will solve harder problems. You can use more quantifiers and build more complexity classes. So a third quantifier is for most strings, right? You may ask whether for most strings something is true. So that gives you BPP. But then when you mix these three, for all there exist, then you will get a lot more complexity classes, and there we have to then discuss what is the meaning of interaction. Okay, so let me give you a crash course on this. This is usually covered in detail in the first course on complexity, but we will not be needing everything here. Let us just go into the definition. Hopefully you will get some insight or some intuition from the definitions. So first, quantifier based. So there exist and for all. So you can define sigma 0 to be the complexity class P, okay, and sigma 1 the complexity class NP. Then you can define sigma 2 to be the complexity class NP with NP as an oracle. So NP to the NP. Okay, so this is like a non-deterministic Turing machine which is using SAT as an oracle. And then you can repeat this process to infinity. So sigma 3 will be NP to the NP as an oracle. Okay, so you get NP to the NP to the NP and so on. So that is a language L is in sigma 2 if there exists a polynomial time NDTM, non-deterministic Turing machine, using SAT as an oracle. So think of somebody giving you a subroutine that solves SAT. So using that subroutine, what can you do? What can an NDTM do, right? So those problems are these sigma 2 problems. Now, why did I call this quantifier based? So actually it can be shown that this problem L which you are solving in the sigma 2 style, an alternate classification of this is, or characterization of this is, that there exists a polytime Turing machine N such that for all input x is in L, if and only if there exists a y1 string for all y2 string n at x y1 y2 is equal to 1, where y1 and y2 are not too large. Okay, the size is polynomial in the input. Okay, so let us read this again carefully. So what this alternate characterization is saying is the problems you are solving by sigma 2 or in sigma 2, these problems have a characterization based on quantifiers, where you will use both the quantifiers, there exist and for all. Okay, so some string x is in L, or it's a yes string, if and only if there is some y1 such that for every y2 n accepts. So this is the important part. If this for all y2 was not there, then it would have been just NP, right? There exists y1 such that n accepts. But with this for all, this is something else. It's a class stronger than sigma 1. So without this, you get sigma 1. So the reason why this is happening is, one intuitive reason is that when you look at NP to the NP, NP is using SAT, but then you can also think of it as NP using complement of SAT. What is the complement of SAT? So complement of SAT are satisfying assignments which are always true, right? Tautologies. So instead of there exist, you can think of the dual which is for all. Okay, so sigma 2 actually is using both there exist and for all. So from NP to the NP, you can actually use this intuition to give a formal proof of this there exist for all characterization. Okay, so informally we can write it as sigma 2 is equal to there exist for all polynomial time. Or maybe we first start with sigma 1. So sigma 1 is there exist P, and sigma 2 is there exist for all P. Okay, this is a simple way to understand and remember what we just did. So you saw the definition of sigma 1, sigma 2. Sigma 1 is there exists quantifier, so you guess and you verify. Sigma 2 is there exists, which means you guess, but then the verification is more complicated here. The verification is for every string y2, the thing has to be true. Okay, so the verification is more complicated than sigma 1, and we can obviously make it more general. So we can say sigma 3 is defined via alternating 3 quantifiers. So there exists y1 for all y2 like sigma 2, and then there exists y3 also. Okay, so the verification is happening in a more complicated way, which is this part. So you have to first guess a string y1, and then you have to verify for every y2 whether there is some y3. Okay. So again, informally you can think of this as there exists for all, there exists P. So we have defined these infinitely many complexity classes in two ways, right? We defined sigma I as a tower of NP, NP raised to NP raised to NP, and we are claiming that there is an alternate characterization, equivalent characterization, which is by a tower of quantifiers, alternating quantifiers, which is there exists for all, there exists for all, and so on. Okay, so remember these two definitions of sigma I, and once you have these sigma i's, so it's basically a generalization of NP. Once you have sigma i's, you can look at the union of this, which is called polynomial hierarchy. And it is shortened to PH. So this is union of everything, all the sigma i's. So this is, you can think of this either a constant number of NP tower of constantly many NPs, or constantly many alternating quantifiers. They exist for all, right? Any problem that you can solve this way is said to be in PH. Now what you can show, it's easy to show that polynomial hierarchy is completely contained in P space. How is that? Well, so sigma's 1 is NP, right? NP is contained in P space because you can go over all the string y1s. Now the first question is, why is sigma 2 in P space? Right? There exists y1 for all y2. Why is this thing in P space? So again, you can actually enumerate over all y1s, all possible y1s, all these small string y1s, and once you fix y1, then you can go over all y2. So that is the proof. So systematically go over all the possibilities of the quantified strings y1, y2 and only constant many times to yc. So going over all the possibilities of y1 to yc systematically requires only polynomial space. Polynomial in the size of x. Okay, so in P space you can solve anything that can be solved by PH, which is essentially saying that any problem in sigma I can also be solved in P space. It's equivalent to saying that. So this is a large number of complexity classes that we have created, generalization of NP, and obviously all these questions are open questions. Whether sigma 0 is smaller than sigma 1, is smaller than sigma 2, is smaller than the polynomial hierarchy, is it smaller than P space? Okay, this tower, this infinite tower, is it collapsing or are things equal? Okay, these questions are open questions. And sigma 0 is P. Even that question is open. Okay, whether P is different from P space. This is also an open question, although P space seems to have very difficult problems which we don't expect to have polynomial time algorithms, practical algorithms, but still we don't have a proof of the strength of P space over P. Okay, this is an outstanding open question. Okay, so that finishes the discussion about quantifier based complexity classes. Next time we will start another or analogous tower based on some other quantifiers. The starting point would be for most quantifier. So third quantifier that we can use is M, okay, which is for most strings. So let us define it. So this statement M quantifying a string y. So My, let's say in the space 0, 1 to the n. So we say that Ny is equal to 1. So think of n as a Turing machine. We say that Ny evaluates to 1 for most strings y. Okay, we say this is true if the probability that Ny is 1 in the space 0, 1 to the n, this is high, let us say 3/4. Okay, so which in simpler words, if Turing machine n is true for 3/4, at least 3/4 of the strings in the space, then we say that n is true for most of the strings, and for that we use this quantification my or quantifier my. Okay, so this is what we have defined as a third quantifier, and using this quantifier with their exist and for all, we can actually define more complexity classes. We'll call them interaction based complexity classes. We'll see next time why this can be seen as an interaction between two parties.